Now I'll walk you through this sample problem, balancing masses on a ramp. So we have two masses here. One is 6.7 kilograms. It's on a ramp that's angled at 42 degrees from the horizontal. It is a frictionless inclined surface. So no friction to worry about here. We have the slope. We have this connected across a pulley to another mass that's hanging there. And we are supposed to find out what that mass needs to be so that the system will be in equilibrium. And for it to be in equilibrium, that means the sum of the forces in each direction has to be equal to 0. Okay, this is getting complicated now. We have so many different things working together here. It's in equilibrium. So in equilibrium, we know the sum of the forces has to be equal to 0. How can we use that? Do I want force vectors? Do I want x or y or parallel? Or what do I need to do? Not really sure yet. So let's see. What else do we have? There's a pulley. We've dealt with pulleys. And we know, I drew that red string around there. That string, whatever the tension is here, has to be equal to the tension there. I want to find M to keep this thing from moving. Actually, this looks like a simple area of the diagram here. Let's start on that. So if I consider just this to be my system, sum of forces on that system, this M is hanging here in equilibrium, right? The whole thing's in equilibrium, so this piece also should be in equilibrium. So if I make a free body diagram for that mass, I know we've got gravity, mg down, T always pulls, right? So it's pulling up, and that's it. So the sum of forces equals 0. I can use that here. The sum of the forces equals, if this is the positive direction, so that's T minus mg, and that has to be equal to 0. So we know that T has to be equal to mg. Okay, I know G, I don't know M, that's what I'm looking for, and I don't know T. Can I find T? What if I consider this as another system? So if I consider this block as a system, and I make a free body diagram of that, I have mg, I have T, I also have N. Can I figure out from this what T has to be? Well, since it's on an incline, I want to think about the force parallel and the force perpendicular. What do I really want to know here? What I really want to know is T, so that's the parallel direction. So that's the first thing I'll think about. We may end up having to go back and doing the perpendicular side too, but I know we need parallel. So let's do that. So sum of forces parallel is, well, if I make this the plus direction, then T is that way, and down this way, let's see, so T was that way, down this way part of mg. N is perpendicular to that, so it's not in there, but part of this mg is there. So that's m times g times sine of theta. And this mg, if this is the positive direction, this mg is made up of one pointing part this way in the parallel direction and this way in the perpendicular. So the part of mg that's parallel is pointed down this way, so negative. So T minus mg sine theta has to be equal to 0. So that means T is, now this M, maybe I should give it a different name. M 6.7. So the 6.7, so M 6.7 G sine theta. Now I know I'm looking for this m, and I have this. So these t's are the same. This must be equal to that. So the m that I want times g has to be equal to, this is 6.7 kilograms times g times sine of 42 degrees. G is on both sides, so those cancel. So that means m equals 4.5 kilograms. Okay, does that seem like a reasonable answer? 4.5 kilograms pulling down here, would that be enough to hold up 6.7? That seems about right, because it should be roughly the same amount, but it should be a little bit less, because this is on an angle, so the tension here to hold this one up is not as much of this mass as this tension has to be, because this one has to hold up the whole mass. So it's a reasonable answer.